Welcome to Old School Chemistry. Today we're going to do the ALEKS topic, predicting relative forward and reverse rates of reaction in a dynamic equilibrium. I want to remind you of the definition of equilibrium. Equilibrium is when the forward rate, so reactants changing to products, equals the reverse rate. That's products converting back to reactants. We have equal rates, and rate is going to be the change of concentration over time. When the rates, forward and reverse, are equal, you're at beautiful, beautiful equilibrium. So let's look at this problem. It says methane and water react to form carbon monoxide and hydrogen like this. They give us the chemical reaction. So we have methane plus water produces the carbon monoxide and the hydrogen gas. Then they give us some numbers, some information. It says imagine 151 millimoles of the methane and 151 millimoles of the water are added to an empty flask. I'm so glad that we got this one first. We'll do this one a couple of times. The empty flask is unique, and you will see it about every third or fourth question. Okay, it's added to an empty flask. So I want you to imagine an empty flask, and we're going to add these two compounds to it. And then answer the following questions. Okay, it says, what is the rate of the forward reaction before any of the methane and the water has been added? Our options are 0, greater than 0, but less than the rate of the reverse reaction, greater than 0, but equal to the rate of the reverse reaction, greater than 0, but greater than the rate of the reverse reaction. Here's what's special about the empty flask. If you just have the empty flask, we haven't added any of that methane and water to it, guess what? There's no reaction. And so the answer on this is 0. And this is the only time that you can put 0 is when you have that empty flask. So I'm going to put 0. All right, now number 2. This is the one where you have to think the most. There's 4 questions. The second question is the one where you really have to think. It says, what's the rate of the forward reaction just after the CH4 and the H2O have been added to the flask? So I like to use a teeter-totter with my students. Let's say that here's my beautiful teeter-totter, completely in balance. This would represent equilibrium. Forward, reverse rates are equal. Well, I have an empty flask to begin with. And so when I add the reactants, the water and the methane, it's going to go crazy like this. Really, really heavy on this side. You're going to have a ton of reactants and not very many products. And so this down here, because you have such a high concentration, so many of these, you have a ton of collisions, a really fast rate. And it's going to hit, collide, and react until it goes into equilibrium. We know all systems, they will reach equilibrium. If they form an equilibrium reaction, they're going to always go to equilibrium. They're the most energetically favorable at equilibrium. So to start, if I have this empty flask and I put all these reactants, you have a ton of reactions, a really fast reaction rate happening here, and not very many of the products reacting. So take a look at this with me. Let me read it again. What is the rate of the forward reaction just after we add all of this? Well, the reaction rate is crazy fast. And then we compare it. So we know it can't be 0. You only use that at the very beginning when you have an empty flask and nothing's in it. Now here, this rate is going to be much, much faster. This is your forward direction. Reactants to products is going to be much faster than the reverse. That's the products back to reactants. So your answers right here is going to be greater than 0 and greater than the reverse reaction. So my answer, in fact, I'll click it, is right here. Let me draw something for you. So if I do my little teeter-totter example, here I'm going to have a lot of collisions. So whichever side is lower, meaning you have more of that substance, more reactant, more product, is going to have the fastest rate. So when we're like this, that's going to be the fastest rate. And over here, this would be the slowest rate. Now, what you have to add to this is the direction. And this is a convention that as chemists we use. We say going from left to right is going to be your forward. So that's reactants to products, and then going right back to left, we call that the reverse direction. And that's when you go from the products back to the reactants, okay? In fact, you know what? just to keep convention, let's do this. Products back to reactants, like that. So one more time on this one. This is where we have to think. I had my empty flask, nothing's in it. I put reactants. Oh, so many reactants, tons of collisions, really a fast rate. So the forward rate, right, going from reactants to products, so much faster than the reverse rate. Now the next two questions are going to be easy, and you'll see a trend as you do more of these questions. The third question, it will always ask, what is the rate of the forward reaction at equilibrium? Well, I react until I consume reactants, making more products, until boom, we hit equilibrium. The forward rate equals the reverse rate. At equilibrium, again, what do we know about the forward and reverse rate? They are always equal. They are always equal. And you'll find that on this problem, that the third question, it always says, well, what happens when they reach equilibrium? Well, at equilibrium, they are equal rates. Okay, our last one. And you'll also see a theme, a pattern on this question as you do more problems. Question number 4, it says, how much of the methane is in the flask at equilibrium? So none, some but less than the 151, exactly 151, or more than 151. Here's the reality. You start with 151, you're going to consume some of it as you make the products. So some of it's consumed, but you'll always have some of it there because the reaction is dynamic, where it's going forward, and then it goes back and it makes some more of the methane. So your answer on this one always will be some but less. You'll have some of it left over because this is going forward and reverse. You're going to have always some of the reactant, some of the products. It'll never be consumed. It's not a completion reaction. You won't have what you began with because some of it will be consumed. And you're not going to have more. That would be against the conservation of mass. So here, the answer is always some but less. Okay, we will check it. And let's do another one together. Okay, so we will read our problem. Ooh, they give us the Haber process, famous equation here. We have 72 millimoles of NH3 are added to an do you know what? We're going to do another one. I do not want another empty flask because that's a unique one. You'll only get that every couple. Okay, good. You'll see a lot more of these types of questions. Oh, we have a big problem here. Acetic acid is going to react with water, so this is just vinegar and water, to form a hydronium ion and the acetate ion. It says you have 196 millimoles of the acetate ion. Ooh, these 196 millimoles are removed. Okay, let's pause right there for just a second. Those are going to be removed. You're thinking, how does this impact equilibrium? Look at this. It's removed from a mixture of all 4 of these at equilibrium. Sorry, that's written over that. It's at equilibrium. Okay, so think this out with me. I'm at beautiful equilibrium. I'm going to remove some of the reactant. Think teeter-totter. If you're thinking the little teeter-totter that children play on, if a child jumps off the teeter-totter, what happens? It goes like that. This side is light. Now, using this principle, if I have more products than we should at equilibrium compared to the reactants because it went like this is going to react faster. Whichever side is lower reacts faster. It has more collisions. So this is going to react faster. So you and I just talking. I know that the forward rate is slower than the reverse rate because we went like this. Again, we are at beautiful equilibrium. We remove some of that reactant. Because I removed some of it, I don't have enough. It tilts like this. I have too much. I tell my students it freaks out. It has too many products. So this is going to react faster, faster reverse rate, slower forward rate. So with that in our minds, okay, we thought it out. Let's answer these questions. It says, what is the rate of the forward reaction before any of the acetic acid has been removed? Well, they tell us before we remove any, we are at equilibrium. So if I'm at equilibrium, what do you know about the forward and reverse rate? They're equal. So your answer right here is, if you start at equilibrium, the forward and reverse rates are equal to each other. I'm focusing on that word right there. Okay, second part of the question, this is where we think. It says, what is the rate of the forward reaction just after the acetic acid has been removed? Okay, so we were like this. We remove that acetic acid, goes like that. So that means the forward rate is slower. the forward rate is less than the reverse, because this is the low, that's the fastest. A lot of collisions are going to happen, freaks out. So our forward rate is going to be less than the reverse because it's higher. The reverse was lower. We had more of those products. We're going to have more reactions. Okay, now look at this. It's going to be very similar to what we just did. The part 3 of this, it says, what's the rate of the forward reaction when the system has again reached equilibrium? So we're like this. The reverse rate speeds up, lots of collisions. It's going to go back into equilibrium. Always, everything in nature goes to equilibrium because it's the most energetically favorable, most stable. So I'm back at equilibrium. What do you know about the forward and reverse rates? They're equal. So here I'm going to say the forward rate is equal to the reverse because we're at equilibrium. So we'll do equal. And then fourth part of the question, how much less acetic acid is in the flask when the system has again reached equilibrium? The answer is always some but less. If we remove that 196, the products, they're going to make more, but we'll never get back 100% to that 196 because we removed it and then we had to make some until we hit the beautiful ratio of reactants, of products over reactants when we're at equilibrium. So always easy peasy, some but less. Some but less. Okay. Good job. Of all the problems that my students have in this particular unit, this is the hardest question. Spend some time, do this extra. Proud of you. Please like and subscribe if you haven't, and I'll see you next time. Thanks.